Hello, everyone, and welcome to today's webinar on electric tankless water heater design. My name is Danielle Swanson. I'm going to be co-hosting today. Leading our discussion today is David Tverziak. He is Hubbell Water Heaters Midwest Regional Sales Manager. Just to let you know, a recorded version of the webinar will be available on our website after recording. And now I'm going to hand it off to Dave. Thanks, Dave.
Thanks, Danielle. Yeah, just to echo that, this is a CEU course for ASPE. However, a stipulation with ASPE, this is for live presentation, you're able to get your CEUs. So at the conclusion of the presentation, if that's something you are interested in getting, please contact us and we'll have those sent out to you. If you're watching this as a recorded version, unfortunately, it's a good technical presentation, but CEUs are not available from the recorded version. So that said, if you're not overly familiar with Hubbell water heaters, I assume most of you are since you're on here today and you were contacted via Hubbell. Hubbell is a manufacturer of engineered water heaters. We do gas, electric, steam, boiler water units, tankless units, storage units, and a lot of custom products out there. Really, the intent is that we want to recommend a product for applications, not because it's the only product that we make, but because it's the right product for the application. And so if you have any questions about Hubbell in general, want to speak to us about specific applications or products, please feel free to reach out. You can get more information on our website or through your contacts and regular sales channels. Now, diving into today of electric tankless water heaters, as I mentioned, Hubbell's MO, if you will, is we want to recommend the right product for an application. And our topic today is electric tankless water heaters, and just a little bit about my background in the presentation today of why I think it's important. My background, previous life, was spent in the world of electric heating controls. In the manufacturing of specifically elements, process heating systems. And during my time there, had the opportunity to work with a variety of water heater manufacturers, providing different components to them. And, Hubbell being one of them, that's how I came to be here, but not the only one. And so I had an opportunity to work with a variety of different water heater manufacturers during that time and see how some of them do different things. And the reason that's significant is in the world of tankless in particular, there's certain things that are kind of left behind the curtain, if you will. I mean, if you're looking at storage water heaters and you were to say, hey, I have this spec for a storage water heater, and you put your performance together and then you send it out to the world, you get quotes back in, the contractors come to you and say, well, I've got this quote and it's for a glass line tank version of that product. And then this quote is for a cement line version of that product or a stainless version of that product. But functionally, they operate really the same way. You'll see price differences and lead time differences. These things are all generally pretty well understood because there's a general understanding of you pay more for this version of it because of longevity or quality of a product or different things, depending on the demand that you're going to see. But when it comes to electric tankless, I know nobody on this call ever does this, but there's a lot of times where we'll see specifications that are left, frankly, very vague in wattage, voltage phase, flow rate and a temperature, and that's pretty much it. And when you have those vague specifications on tankless products, what ends up happening is you get a manufacturer that supplies a bid that is in line with your spec, and they'll say, all right, you can buy this tankless product for $300. And then you'll get another bid for the same spec that says, hey, I'm also meeting the spec, but I'm $1,000. And so you have this big gap in cost. And as a manufacturing community, we haven't really done a great job of explaining why that is. It's easy to say, some folks might say, oh, well, you get what you pay for. And such and such brand is no good, or such and such brand is really good. The reality of it is no manufacturer comes into this and wants to put something out in the market that is a piece of garbage, or that is it's a throwaway product. Nobody comes into the market with that in mind. All the manufacturers come into the market and say, I have a solution that I believe is a good fit for a niche or an application, or maybe I can do something better, more efficient. There's a variety of reasons that they come in, but we all come into the market with the intention of providing a very good product. And the reality of it is, with some of these products, some of them are more flexible than others in terms of what you can and cannot do with them. And so the reason that we're going to dig into this today is, again, Hubbell manufactures a variety of products, and being out in the field and talking with customers on applications, I've had multiple walk downs where I've suggested, a tankless product would be really good here. And I've had customers come back and say, you know what, I've had bad experience with electric tankless. I don't really like that technology, or they tell me their stories of what went wrong, why they don't like it. And as you start peeling back the layers of the onion, what ends up happening in most of those cases is, a product was put in here that really should have never been in there in the first place. It operated the way it was intended to operate, but it led to early failures or poor performance. And, that's not the fault of the manufacturer. That's the fault of us as a community of not fully understanding the products and not specifying them accordingly. So that all said, our goal today is to really talk about the tankless products in the market. What's in these things? How do they work? What makes the different brands different, different styles different? And what's that impact to not only the project, but the applications and what you can do or not do? And ultimately, what features do you need to specify to make sure you have proper operation during these projects? So without further ado, when folks think of tankless water heaters, this is kind of what they imagine. Cold water comes in, hot water comes out. There's no tank, ergo it's tankless, and there we go. That's it. Pretty straightforward. But if you remove the covers on these products, there's a variety of things that you can see. And in some cases, you have scenarios such as this where there's frankly a lot going on. It's more of a heater system and not just a component, not just a heater. In this example here, I won't read everything to you, but you've got a flow meter where you're measuring your flow rate. You've got inlet and outlet temperature sensing. You've got safety high limits in there. You've got solid state switching, digital controls. You've got all these features going on to make this product operate and adjust based on that application that you're working on. Now, when you leave a spec vague in the sense of just, those basic data points I mentioned, what ends up happening is you're dealing with the bookends of the industry. Product on your left, obviously you can see there's a whole lot more going on, very similar to the diagram previously. The product on your right is in a category that sometimes is called flow-controlled tankless products. And that name of flow-controlled tankless product is a little bit misleading because they're not actually flow-controlled, they're flow-activated. In fact, the way that these products in some cases operate is the only control device is a flow switch. So it says, do I have enough flow that I think it's safe to turn on? Yes. Okay. Switch closes, contacts energized, and your element turns on. The only temperature sensing device in some of these is a safety high limit that is actually not even measuring water temperature. It's a surface mount sensor to make sure that in some products they use a thermoplastic chamber, which there's nothing wrong with a thermoplastic chamber, but they want to make sure that it doesn't melt. If you recall, those of us that have been around for a little bit, there was a period when, some of the tankless products in the industry, people would say, like, it got so hot, the element came right through the side of the chamber. There was a learning curve for different manufacturers using those thermoplastics, and this is partly how they addressed that, was to make sure we control these things so that they don't self-destruct. Now, that's not measuring water temperature at all, right? So it's, to call it flow controlled, again, it's flow activated. And so if your specification is vague, you've got these two products, which are your bookends of one that's got all the bells and whistles and one that has none, that can both be offered here. And so it's worth noting that the industry is filled with products, not just on these ends, but that have varying features in between them. And so for our discussion today, we're going to kind of focus on the bookend discussion, but understand, the features we're going to go into. You have some products that might have certain features of one and combined with the other, and it's not all or nothing, but it's up to you to understand what features are important for your application. So with that said, in terms of what these products in the market all have in common is the two major components that all of the electric tankless have in common are elements and power controls. Your elements, electric elements are just basically big resistors. That's, your currents, your electricity is coming through them. They're generating your heat. That's how it's getting applied to the water. Power controls, if you don't have an electric background, understand, and I'm going to say this multiple times, power controls are different than temperature controls. Power controls are devices that take power coming in and they apply it. By themselves, they are the brawn, they are not the brains. They are the method of applying it, but they need something else to tell them how to do it and when to do it. So with that said, even within these product categories, there are differences. So the first thing we're going to talk about is the elements. The elements used in electric tankless products for the commercial world are generally going to be an open coil element or a sheathed element. Like everything in life, there's pros and cons. There's reasons for both of these options. First things first, the open coil elements. You'll see these very, very commonly in tankless. And the advantages of the designs using an open coil element are that, number one, they're frankly a pretty inexpensive product to make. If you look at you can see it a little bit more clearly in the top example, but it looks kind of like a slinky that's going back and forth through those ceramic spacers. That's your nichrome wire. That's your open coil heating element. That's what's generating the heat. And so there's, the devil's in the details, of course, but in terms of the cost to manufacture, they're relatively inexpensive to make. So that's a good thing. The other thing is you can pack a lot of heat in a very small space with these designs. So again, a lot of tankless installations, you're looking for, how do I save space? So that's good. The drawback and the reason that everybody doesn't just use them is that by comparison, open coil elements are relatively fragile. And so there's a lot of different reasons why an element can fail. And if you had a failed element, you sent it to a manufacturer, we might give you a variety of responses of what we're looking at of what caused this failure. But in terms of open coil elements, there's a lot of culprits, but they generally lead to one common failure, which is a dielectric short, an arc that happens. And so the way that these elements will fail is, again, if you imagine having a slinky sitting on your desk, if you pulled your slinky across the desk, you've got this nice coil, you've got relatively consistent spacing, and it stays there. But if you took that slinky and you turned it vertically, it would sag towards one end. And that is the same phenomenon that happens with open coil elements. Is every time these things are energized and they heat up and they cool down, you get a thermal expansion and contraction that's happening repeatedly. But the lower image there, you can see the coil kind of goes down, and you can't see the backside of it, but it loops and comes back up. Well, your water flows down the path of that coil. That's really good for heat transfer. That's why you can make them relatively small. But what happens is every time these elements are cycling, the water is pushing down against that coil. It's pushing it all in one direction. And so after extended repeated use, it's going to tend to push the coil down. The spacing gets smaller and smaller. And as those highs and lows, if you will, if you imagine it like a sine wave, as they get closer, you'll eventually get an arc that goes from one peak to the next peak because the spacing's off. And that's your short, that's your dielectric failure. That's what causes it. Now, the major culprits to that make it happen faster are, number one, if you have a high pressure system or really high flow rates, that's going to tend to push against these coils and lead to earlier failure. Similar to if you've ever been water skiing versus walking down the street, if the wind is blowing at 10, 15, 20 miles an hour, you can walk along and you'd say, wow, it's pretty windy. But if you're down in the water, you're trying to get up on skis. I'm not a very good skier, but I've been drugged behind a boat plenty of times, and that boat going 10, 15, or 20 miles an hour, if you're in the water, the amount of pressure against you is it's everything you have to hang on to it, right? Well, that's the same phenomenon here. Is water is pushing down against this coil, the more flow, the more pressure, it's forcing that coil in one direction. The other thing is if you have really poor water quality, or if you have hard water, these type of elements, you're going to get scaling and calcium deposits that are just bound to happen in some degree. That creates drag and it acts like a sail on a ship. So if you have hard water, these type of elements are going to tend to fail faster. They're going to tend to deal with that scale poorly. Now, again, that's that trade-off there. Now, the next option is a sheathed element, and by comparison, there's a few different ways manufacturers will make sheathed elements for tankless products. There's cartridge designs, tubular designs. We won't get into all those details of how they're different. The point being is that where they're the same is, again, you're using a resistance wire to generate your heat in the middle. It's compacted with a magnesium oxide, a dielectric insulator to prevent the arcing, and then it's compacted down with a metallic outer sheath. Now, typically in tankless applications, these elements are going to be made of stainless, titanium, ink alloy, Inconel in some cases, not as common, but the reason people use sheathed elements is the exact opposite for using open coil. Is they are a more expensive product and they are a bigger product, but they're also very robust. So these types of designs will tend to handle hard water better, high flow rates better. You know, they're as that magnesium oxide gets compacted around the coil, it's, you know, for practical examples, think of it as putting a wire down in cement and letting it cure. It's in there, it's not moving. So it's a very robust design. But again, with that, it becomes a bigger product. It becomes a little bit more costly. So to say one is better than the other really depends on your application. Again, if you have something that's going to be very infrequent use, remote, low flow rates, will an open coil element design last? Sure. If you're going to have more wear and tear, you know, sheath elements will tend to last longer. So just to liven things up a little bit, we're going to offer just a couple of quick polling questions as we go. So with that, I'll launch the first one here for your consideration.
If the application expects you to see high flow rates or harsh water conditions for optimal element lifespans, you should consider using A, open coil elements, B, sheathed elements. And as a note, we will be accepting questions and answering them at the end of the presentation. Feel free to enter your questions into the chat box that's offered on the screen, and we'll try to get to everybody's questions at the end.
And feel no pressure also on these polling questions. We're gonna try and gather feedback. We're not gonna push back on anything here, but you know, again, more for discussion. All right, we're gonna go ahead and close that up there. We're not gonna let it run for too long. So yeah, I mean, if you've got harsher applications, your sheathed elements are just going to last longer in these type of installations. Now, as we move from the elements into the other devices, the power control devices. Now, power controls, there's a whole lot of different options that can be power controls. There's contactors, there's relays, there's triacs, there's SCRs. At the end of the day, all the different products that exist in the power control market can be bucketed in one of two categories. You have on-off style power controls, which is similar to your contactors, and you have modulating type devices, your relays. Now, in very practical terms, power controls by themselves are kind of like, you know, switches in your house. If you think about the dimmer switch that may be in your dining room, that's a modulating type of power control. That means that you're able to adjust how much power you're putting through to get a desired result. And, you know, in the case of your dining room, maybe light bulbs are just small resistors, heating elements are big resistors. You know, maybe you want 50% of the capacity there, or some amount where you want, you know, mood lighting. You can control that. Contactors, there is only on at 100%, and then there is off. That's like a light switch. When you turn it on, it's just on. That's how these devices work. Now, as I mentioned before, power control devices are just a method of switching. They are not temperature controllers. But if you were to pair a temperature controller with a power controller and graph those results, here's what these tables would show you. This is what it would look like. Is On your left, if you have a modulating power control device, I'm trying to maintain 105 degrees. The temperature controller would be sensing that and saying, hey, if it's below 105, I want more. If it's above 105, I don't need it. And so what happens is it's calling for heat until it gets up to set point. And it's very common with a relay type device that you get a small overshoot or it bumps up, but then it starts pulsing very rapidly is the way that these things work. And it's constantly measuring that temperature and constantly feeding back, do I want power or not? And so it's responding very quickly with the intent of holding it at exactly 105. If the demand slows down, the pulses slow down. Again, it adjusts as it goes. Now, if you were to be using a contactor in that same installation, the same temperature controller says I want to maintain 105. The way that it would function with a contactor or on-off control is it would turn on until it hits 105, and then it would turn off. And then when it drops down to a certain temperature, it would turn back on. And so you get this sawtooth graph. Now, that distance that the temperature drops is called the dead band. And you can adjust the dead band of these products, and you can make a contactor actually act like a relay. However, the reason that you don't do that is that when contactors are made, they are made with the intention of hundreds of thousands of cycles for their lifespan. And that seems like a lot, but if you were to tighten that down and have this device switching every second or multiple times a second, you can imagine you're going to get through your hundreds of thousands and into a million pretty quick. It's going to happen faster than you'd like. And so relays, on the other hand, are typically made with the millions of cycles intended as their lifespan. So similar to the element discussion, there's reasons that both of these devices exist. When you're doing an application that you're very concerned with specific temperature, a relay and a temperature controller is going to be your better solution because you know exactly where you're at and how this is going to be there. It's going to be more accurate. It's going to last longer. Contactors are going to be less accurate and not last as long, but the trade-off is they are more economic. So similar to the elements, again, if you have a application that you know is going to be very demanding, considering a modulating type power control and temperature controller is going to give you more lifespan, more accuracy. Yes, it will cost a little bit more, but again, that's the trade-off for your application. Now, again, I've said it multiple times, I'll say it again. Power controls and temperature controls are not the same thing. And so if you think about the different types of tankless products that are out there, I mentioned earlier is the flow activated tankless products don't have temperature controllers in there. So a question that sometimes comes up is, okay, so if you're telling me that device does not have temperature control, how is it sized? How is it used safely and properly? And so it comes down to math and it comes down to theory. Now, I use this quote from Mr. Einstein here, not because a flow-based tankless product is a bad product. What it comes down to is if you're using a tankless product that has temperature controls and modulating power controls built into it, it can handle a variety of applications. It can be overkill for some, but it will function, it will work, and it will last. In most of the instances where I've seen products misapplied, it has been in the group of flow-based products because the idea behind it is, well, it has the same power output, and so I'm just going to use this here because it's a less expensive design. And then inevitably what happens is those products fail prematurely, people get frustrated. So I'm going to dig into those products a little bit here. Again, that's not because they are a bad product, it's because they are prone to misapplication, whereas the other side of the spectrum, if you can't really misapply it, you might put in something that's overkill, but it still works. Again, where these products, flow-based unit, you can misapply that. So the way that these products are sized and the way that you approach them in the market is based on flow rate, right? And so the industry as a whole, we all kind of agree on a standard set of math, big surprise there. We say, all right, look, if I'm going to size a tankless product, I know I need my flow rate, I need my temperature rise, and we agreed on this constant to get our KW. Make math pretty simple. So if I have a 0.5 GPM fixture and I wanted a 56-degree rise, that means that I would size it and I'd say, hey, I need 4.1 kW for this installation. And the industry as a whole would agree on that math. And so seems easy enough. But where this gets a little bit tricky and prone to premature failures is this little feature right here. In this particular graph, it's called a turn on GPM. Some manufacturers call it the activation flow rate. But what it is the minimum flow rate that is required for this product to energize. Now, again, electric elements are just big resistors, so they don't change their resistance as they go. So if I have a consistent resistance and now my flow rate changes, I'm now solving for X, which is temperature rise, which means this product that I sized at 0.5 GPM for a 56-degree rise, if it only sees 0.3 GPM, which is enough to turn it on, it will give me a 93-degree rise. Now, this is significant for a few reasons. Number one, the obvious is that's way more heat than you are bargaining for. And so as a side note, I will say not all code requires safety mixing valves. But if you are using, in all applications, but if you are using a flow-based tankless product, it's very important that you have a safety mixing valve there because of this very basic phenomena, which is it does not have a temperature controller. And as I mentioned before, the safety high limits are not always measuring water temperature. So you need to understand that that product, depending on the flow rate, can give you a variety of temperatures. And as practical examples here, if you're using a fixed flow fixture, remember back long ago when we used to travel and go to airports or go to restaurants, you'd go into use a facility, you'd wash your hands, you'd walk up and you just wave your hand underneath it. That's fixed flow, right? Every time it detects motion, that fixture is going to turn on and it's going to give you a certain flow rate. I know what that flow rate is going to be every time. But if you went into a facility and, let's say that as an engineer, you're working with a customer who says, you know what, I really like those nice gooseneck faucets with paddle handles, where the user has the ability to reach up and change that flow or change that ratio of hot to cold. What you've done is given the user the ability to cause your heater to fail. And if anybody else is like me, if I walk up to those type of fixtures, instinctively, I grab the hot water valve every single time and turn that on first. Because my assumption is I want warm water, and a lot of times things come through and it's not quite warm enough. But if it happens to be too hot or hotter than I'd like, there's one of two things that happen. Either I grab the cold and I turn that on more, which the fixtures that we're using today aren't adjusting their flow rates necessarily. So you're changing that flow going across the element. So if I turn it on and it's hot all the way, let's just say I've got 0.5 GPM. As soon as I start to add cold, it's throttling back the flow across that heater. And as that happens, the temperature of the water coming out of the heater is actually going up. And so I either continue to add cold or I start to push back and reduce the hot. In either scenario, as that flow rate drops, these products are going to run into one of two inevitable things. Either the flow going across the heater itself drops below that minimum flow rate and then it turns off. So you go from hot to kind of warm to, okay, now I just have cold. Or the temperature inside that device starts to continue climbing to a point where it eventually trips the high limit safety and then the heater turns off again. So in either of those scenarios, by reducing that flow rate from what you sized it for, you're creating more heat coming out of that product. And as that happens, it's going to force these products to cycle more frequently. And that, again, as we touched on with the elements and with contactors, the more frequently these things are cycling and the more wear and tear they see, it's going to lead them to fail sooner. Whereas, again, if you had a temperature controller and modulating power control, as that flow rate changed, the product would throttle itself back intentionally. It would be able to adjust because it's reading the temperature and saying, I need more or less to maintain that. Whereas in a flow-based unit, there's really nothing there that's letting you know exactly what that temperature is. So that said, I will point out now, for point of use applications, this is generally not an issue, but it's worth bringing up just because as an industry, we tend to standardize on 40 to 140. We're sizing heaters, we need a 100-degree rise. That's great with storage. That's great with central systems because you want a little bit of overshoot. Nobody ever complains that they have too much hot water in a system. They might complain if the water is too hot, but in a main system, in a research system, in a storage system, having some extra capacity is not a bad thing. Dealing with these type of tankless products, extra capacity means that it's going to heat up faster and has the tendency to overshoot, which again leads us back to our previous slide discussion, where these type of tankless products, if it's a flow-based unit, you really have to be aware of your feed water temperatures and make sure that you size them appropriately, because you can't just oversize them and then expect them all to work, or at least to work and last. They're not going to work the same. If you use something that has temperature controls into it and you oversize it, not a big deal. It will throttle itself back. But again, feed water temperatures, especially with tankless, are different than groundwater temperatures. It's again, tendencies that we have on main hot water systems are a little bit different here. If you could have a installation at one site, if it's a high-rise building, for example, with 20 stories, well, the feed water temperature coming into your facilities on ground level may be different than the water coming into your fixtures on the 20th floor. So you could put the same fixtures in at the same building and have different performance as you go up, because the water is going to be sitting in the pipes for different amounts of time. And if it comes to those fixtures and it's a difference of a few degrees, that you're not going to notice that. But if it's sitting in the pipes overnight, first thing in the morning, all of a sudden somebody's washing their hands on the top floor. Well, the water in those that's coming into those heaters might be 10 or 15 degrees warmer than it is coming into the other fixtures. And so the products are going to need to know that. They're going to need to adjust as you go. And again, it's not a matter of a flow-based unit can't be used in all these installations, but those type of features are going to cause them to work harder than they were intended to, and you will tend to see them fail faster if you're oversizing them. And again, just to stress it, you should have safety mixing valves in there. Now, before I jump into that all said, I believe we have another question for at this point to share with you all.
If your installation plans to be paired with a varied flow fixture or multiple fixtures from a single heater, for optimal and safe performance, you should consider a heater with temperature controls and modulating power controls, flow activation only. And just as a note, we'll be accepting questions at the end of the presentation. Feel free to leave your questions in the chat box that is provided at the bottom of your screen.
All righty. Yes, if you are going to be putting a single tankless product with a varied flow fixture, or if you choose to have a single heater working with multiple fixtures, you're really going to want to have something that has temperature controls and modulating power controls, because it can adjust to what that demand is. Now, part of the reason for that, again, in the discussion on safety mixing valves, is in my previous life doing process heating applications, we would have our process control set and our safety control set. And without reading to you, I mean, the idea is you have process controls, and because you have a set of parameters you want to maintain. Your safety controls or your limit controls are a separate set of devices that are used to protect your system. That means that if my main set of controls fails me and it doesn't do what it's supposed to do, I have something else there to keep me and my system safe. Can a device be both? I would say by definition, it cannot. I am not a valve guy, and so the discussion on if I use a flow activated tankless that doesn't have a temperature control and then I put a safety mixing valve there, is it still a safety mixing valve or does it become a process valve? That's a question that does come up. I'm not a valve guy. I'm not going to pretend to be, but that is something worth discussing with your valve manufacturers and representatives. And this is the main reason that I bring it up and I push to that is this is a feature within the tankless world that is different than many people expect it to be. And that is your process controls versus your limit controls. Now, let's start with our known here. If you're dealing with a storage tank, you've got a thermostat, and if you that says, hey, I'm trying to maintain 140 degrees in this tank, or whatever your process target is. And if you kind of go through the progressions, the initial feature that manufacturers offer on a storage tank is a surface mount sensor for safety high limit. The idea being, if the water heats up, it heats up the tank, and then the surface of the tank gets hot enough that it trips the safety sensor, and we say, hey, turn off the heat. We don't want to blow our relief valve. We're trying to control it and maintain it, our system. Now, you've got a big thermal mass in that water, and it takes time for that all to happen. And so what we tend to see is as your BTU or your amount of heat increases and or the size of your tank decreases, so that ratio of your thermal mass, how fast can this thing heat up? The next step is we go to an immersion high limit, the idea being we're afraid that the water can heat up too fast that it would trip the relief valve or cause potential harm before the tank frame and everything heats up and trips a surface mount. So an immersion high limit goes right into the fluid and we're measuring more accurately and more quickly. Well, if you follow that same progression and thought process, it would make sense then that folks would assume, well, if I've got a tankless product, my ratio of volume to BTU is about as far over as it's going to get. I've got relatively no thermal mass. And so I need something that's checking this water temperature and responding very quickly because I've got a lot of BTU, higher flow, and no mass. Well, again, when it comes to high limit controls, this is something that the tankless industry as a whole has kind of said, look, with all due respect to you as our customers, we are trying to protect ourselves more so than you. And specifically what that means is a safety high limit or a limit control device on tankless products very rarely is actually in the outlet measuring your water temperature going to the system. They are put in strategic positions within the equipment of manufacturers to say, this is a trouble spot. If this piece of the equipment gets too hot, turn it off because something's wrong. We don't want to overheat and cause failure. Now, you might see some of these safety high limits set at maybe 140 degrees could be put in place. Some of them are as high as 190 degrees. And that's because based on the surface that they're measuring, again, they're not worried necessarily about the water temperature. That's a byproduct of it. They're saying that if this device gets too hot and fails, something's wrong, and we as manufacturers don't want to be sending out replacement units. And so turn the thing off before it fails and have somebody come look at it. And for what it's worth, even if your safety high limit is set at 140, understand that if it's a surface mount sensor, that means that the water temperature inside that's heating this thing up is beyond 140 degrees, because in order to overcome that thermal mass to heat up the chamber to a point where that sensor trips, you have to have something hotter than where it's going to trip. It's thermodynamics. So there are some designs that do incorporate additional sensors in the hot water stream going out. You typically see that on larger capacity units, but your standard point of use units, the high limit safety controls and safety sensors are not measuring your water temperature. And so because of that, that is why your safety mixing valves are so important in those systems. Is if you don't have a temperature controller built in, there's literally nothing that's stopping the unit from producing scalding water to come right out. And so that is something that, again, it's unique to tankless products. It's a little bit misleading because of how storage tanks are done, but if it has even devices in the market that have a process control, if it doesn't explicitly say that its safety high limit is measuring water temperature, those devices are there to protect the equipment and cause somebody to come look at it and make sure something's not wrong, but they are not there to prevent the equipment from producing water at a certain temperature. So, pardon me. So in terms of an overall project, now this is just more of a discussion cost, discussion of cost of where we kind of live. And so I think everyone's tendency is we like to live in our own little bubbles, whether we admit it or not. And if you're working on a project, if you're specifying plumbing equipment, the idea is, well, my budget is the plumbing budget. And this is not a universal statement. We've got people on our presentation here from different parts of the country. And some areas you're going to see plumbing costs versus electric costs that are going to be one ratio. They're going to be different somewhere else. Now, in general, I will say your electrician's costs are going to be more expensive, and your electrical labor, because of wire conduit, required junction boxes for code, electrical installation costs tend to be higher. And so, as a very, very basic example, if I had a lab with 2 sinks in it, I could look at it and say, all right, I've got my appropriate safeties put in, and I can do one of 2 things. If the customer is interested in using tankless products, I can either put 2 lower cost tankless products in, one for each sink, or I can put 1 more expensive tankless product in that can handle both of these sinks. And on the plumbing side of the world, we might look at it and say, well, again, just for discussion's sake, if this is $300 times 2, that's $600. That's still a less expensive device than this $900 product. And that's true on plumbing equipment. That is a cost savings on a job. But when you factor in the electrician's labor of running the additional boxes and wires and conduit, you may find in some areas that it's actually more economic to the project to use 1 tankless product than 2, even though that tankless product might be more expensive. And so again, this is stepping outside of the world of plumbing and saying, if you've got a job where you're going electric tankless, first of all, you've probably already received a piece of hate mail from the electrician who sits across from you because you're using up his utilities. But understand that the costs on the overall project go beyond just what we do. And in terms of responsibility, at the end of the day, like many things in life, you can put things together on your own and save cost. That's reality. And so if I want to put an inexpensive heater, a standalone heater product, and build out valves and different things on a system, that's fine. That is an economic solution, but I have a variety of people who I'm dealing with who are shouldering that responsibility. If I buy everything in a box, whoever's box that is, it's got their name on it, and they're responsible for everything in that box. And so that beyond just what we're looking at here with point of use tankless products, but as we expand into different tankless applications, a common one is for your tepid or safety showers, eye washes, rinses. There's a lot of different ways to put those systems together. Some manufacturers use a mixing valve built into their tepid products for safety. And so it's an all-in-one package that's rated for a safety application. Some do not. On tepid applications, it is worth noting that just like our earlier discussion, there are some manufacturers that offer safety or tepid tankless products that are flow activated at a 10,000 foot level. That seems like a very good pairing for a flow-based unit because you have fixtures that are rated to do a very specific flow rate. So you can size them accordingly. Where you can sometimes have hurdles with that on the tepid side is that a flow-activated product, you cannot recirc through that because it's sized for a certain temperature rise at a flow rate. And code for is going to require you to recirc those lines. And so if you're recircing the lines and you bring it back through that tankless, now the water coming in is climbing in temperature, you're creating water that's going outside of tepid. So bear that in mind if you're looking at safety or tepid applications. You can't just assume that all of these are equal and going to be able to recirc. Some have, again, safety mixing valves, temperature controls, the whole kit and caboodle. Some do not. So that's something you need to be aware of as you're specifying those products. So again, just a bit of a recap here on a couple items. If you've got varied flow, multiple fixtures, you want to use a single heater, use something with a temperature controller and modulating power control. It will perform better, more accurately, and it will last longer. If you have an application with high flow rates or harsh water, sheathed element designs are going to last longer. Again, this does not mean that they're the only solutions. It just means that you will avoid some headaches down the road by doing that. Now, a application detail that doesn't get a lot of press is sound-sensitive environments. So for those who aren't familiar, if you have a modulating power control device, a triac relay, they don't make noise when they operate. They're relatively silent. Contactors are sometimes called click clacks by electricians. They make a snap or hammering sound every time they switch. Now, that's not because they are working poorly, that's just what they do. And the amount of noise that they create will vary based on the size of the heater, based on the amperage going across there, the draw going through these. So there's a variety of contactors in the market that will make different levels of noise. All of them make some noise, but they will make noise, some more than others. And sound sensitive environments can range from doing a wash sink in an OR at a hospital where for obvious reasons, you don't want to create any distracting noise. You might be working at a university with sinks in a lab or in a classroom setting where they wanted to use tankless products there. And so you want something that's not going to create a bunch of noise. The other side of that could very well be a side of, I'll use the term vanity, and I hope no offense by that, but sometimes you're working with clients and customers who just flat out have certain levels of expectations for their own reasons. And so in a hypothetical example, I'm going to show you a brief video here of an installation from an executive bathroom at a facility where tankless products were installed that were using contactors. And because of the amount of noise that was created, the end customer requested everything to be changed out to a design that was more quiet. So without further ado, here's a short video of what that was. So if you, assuming you could all hear that, there's probably two things that came to mind. Number one is whoever set that thing up to run, let it run way too long, because every place I've ever been with a motion sensor to start water, I feel like my hands are still covered in soap before it turns off. But also, I can't believe how loud that thing is. I've never heard one that loud. And again, this is an installation. Manufacturer came in and confirmed that the product was working correctly. This is just how loud it was. And again, that's not every contactor installation, but depending on the available utilities, you might find that even in a lower flow installation, you're forced into a particular configuration that is just going to make noise. And so if that is something that is of concern, if it's in an airport, I've never heard of somebody tracking down maintenance in the airport to say, hey, that sink over in that bathroom was making noise. But certainly if you're in a situation where you're dealing with owners or executives in this case, or anybody who might be sensitive to sounds, that is something to be aware of. So again, these, you could call it a universal tankless design. If you have sheathed elements with temperature controls, modulating power controls, it may be overkill for some of your installations, but it can work for just about every installation if it's sized properly. Your flow-based units are really intended for their best performance to be paired with a single fixture that is fixed flow. Again, it's not that you can't do anything else with them, but sizing them and specifying them in those type of applications is where you will find your best performance of those products. So having said all that, I thank you all. I know we've got a couple of questions that appear to be up there. And so we'll go ahead and take a look at those now. Okay, so I've got a few things that are up here. So a piping diagram for recirc water heaters on a tepid water system. Yep, that's something that you absolutely could get your hands on. I'd say please touch base with your local sales contacts individually. They can get that for you. And should a mixing valve be installed on the outlet of a tankless heater? I would say yes. I think if you're, especially if you're going with a flow-based unit, I would say you absolutely should have one, even if code doesn't require it. You know, if you have a tankless product that has temperature controls and everything else incorporated in there, then I mean that I would say to your local code, you can do it or not do it. The reality of it is, if you've got a flow-based unit, there is nothing there that's preventing not a process control. It does not exist. So it's just a heater. It's been sized. You are applying heat. There's nothing that's protecting the user from hot water. And so if you're using a flow-based unit, I would say absolutely you need a mixing valve. What is our take on Legionella? That is quite a open-ended question. I'll say this, you know, in terms of the Legionella discussions, you know, there was a period of time where folks believed that Legionella was strictly coming from our storage water applications and everybody should be going to tankless and that would stop Legionella. Look, the reality of it is there's a lot of really good information out there. Legionella is not caused by storage applications and it's not prevented by tankless application. Legionella is bacteria in your water. So I'll save that for another, again, discussion that can certainly go more in depth than what we're going to do here today, but absolutely follow up with your local sales contacts and you can get into that quite a bit. I just want to make sure I've got this here. All right, we're accepting questions. All right, so, all right. Have you ever heard of a requirement for a relief valve, a TMP on a tankless? I will say this, we deal with a lot of different crazy things in terms of code requirements and what type of relief valves are required for tankless or not tankless. There's some areas of the country where they might say you only have those requirements on storage systems. There are some areas of the country where I have seen that they say, hey, for any heating product in your system, you're going to need a TMP or such. And so that is one that I think really does depend on your local code. That's something we won't go too far down the rabbit hole here. But you know, in terms of local code, again, that's something that's going to vary from location to location. In some areas, I do know will require it. I certainly couldn't tell you which ones do or do not. In terms of sizing up tankless products, I will we'll pass that along to your local sales contacts to help you out with that. I appreciate the question certainly, but yeah, if you have a application specific question, you know, we can follow up with that and take care of it offline. All right, all right, if there's no other questions here, you know, at the moment anyway, I do want to thank everyone for joining us. If you have questions or think of something after the fact, you know, please do reach out to us directly. We can follow up with you all offline and answer whatever questions you have, help size products, and hopefully put the right product out in your applications.
Thank you for joining us today, everyone. Just as a note, we'll be providing a recording on our website if you're interested in rewatching the presentation. Thank you so much for joining us. Please look out for future webinars in your email box. We're planning on having a lot of them, and we appreciate you all for attending. Thanks.